the properties of random variable. I define this uniquely. It means, let's do that. What is that? In the first line, every name of the attribute is unique. That's the uniqueness of random variable. Then variability or differentiality. Then randomness. Then independence. The independence is not to be explained for variable attributes, different attributes, but for individuals. The individuals in the sample are independent. It means everyone enter into the sample by itself is not it is not determined by all the other individuals. That's the independence. Convergence. That means random measurement is converged. Is converged. To converge to expectation or the measurement, the random distribution. It is equal to a random distribution. Boundary means any random variable measured in a range. If measurement has no range and no centralized location, it is unknown. Relationality, or how to pronounce it? Relationality, or relationality.
Both are fine.
We need this concept in statistics because we do regression analysis. The regression or correlation analysis is for the relationship among attributes. I would like to take attributes from now, not variable. Yeah. Everything in a system must be related to each other in different levels of the strength. If something is not related to everything in a system, it is not in this system. It must be eliminated from this system. Measurability. Probabilities. Yeah, this word exists in the system. It means any variability of individuals in a population occurs in an expected possibility or probability. And the probability itself is a special random measure. The probability itself is a random measure, which is measurable in the bounded range. Axiomatic statement in statistics. I would like to give this. Actually, I gave this presentation at 2009 in the joint statistical meetings. Axiom 1. Any unbiased statistic defined over sample X for a parameter P X can be obtained through its random variable X or attribute X. A set of parameters defined on the random attribute is not equal to a set of this one defined on this, even n is equal to m. If the two random variables are not defined on the same probability space. If they are not defined on the same probability, they are not equal to each other. Axiom 3. All observations of random variable x defined on a random space constitute a single distribution which has only one expectation. Axiom 4. Any single observation xi is not an estimate of the population expectation. It is just a random point. So the median might be an exception. Might be, if we have no other ways to estimate. And 5. If two random variables x and y constitute a joint distribution, an observation xi on x, which randomly corresponds to an observation yj on y, cannot return the expectation y, except in the case that only one observation x and y can be observed for both. This means the optimization in the current system is wrong. It's theoretically incorrect.
By current system, do you mean Kolmogorov system? When you say the expectation is wrong in the current system?
No. Optimization.
Well, the optimization is wrong.
Yeah, the optimization, some optimization, not everyone. Some optimization, because if someone used the optimizer to make a model selection, they usually use the minimum or maximum of the optimizer to make a model decision. We should know the minimum optimizer or maximum optimizer is one of xi, right?
Mm-hmm.
They cannot determine the expectation of the model because the premise of a model is random measurements. They are changed along with the change of the optimizer. Axiom 6. There's a scale or criterion in measuring random attribute. And the scale or criterion must be the same for every individual in the population. This is the so-called measurement consistency. Otherwise, if we don't have this consistency, we'll have systematic error in measurement. Only the measurement consistency can guarantee the measurement error is random, not systematic.
Question before you go on.
Okay.
For Axiom 5, don't most optimizers follow the surface of the space to find a maximum or a minimum for the variables? So that you're saying that that's not valid is really to say that most systems for optimizing are not valid.
Excuse me. Excuse me. Could you please?
Okay, maybe I could talk to you there. I'll talk to you after. Can I ask you this question afterwards?
Yeah, sure. Yeah.
Can I ask a question now? I understand there's a big paradigm shift between current systems or methods as you're describing to what you're describing. But I'm not getting a sense of, like, say the paradigm shift between frequentist statistics where, you know, they're fixed but unknown values constant that we're trying to estimate the population over long-term frequency versus Bayesian statistics where you consider these same quantities random variables. There's some sense of how that paradigm shift actually leads to something that may be advantageous in some situations. What would be the advantageous? What would be something advantageous about working with your system? I don't have a good sense of that from what you're saying here, but that would be a good thing to try and convey to others.
Yeah, I think.
So what would be advantageous of your system versus, say, Kolmogorov's or standard optimizers?
I have to say, I don't have the education background in USA, so my English is very limited.
Okay.
Some words I cannot understand in your statement or in your questions.
Well, maybe I'll go with a quote from a self-taught statistician, George Box. He said, and I tell it to my students here all the time, all models are wrong, but some are useful.
Oh,
So I'm
okay.
trying to say, just in your modeling approach and your system that you're using, what's the useful aspects of it?
What's the...
What is useful in terms of, like I have infectious disease researchers come to me trying to design studies to answer questions they have.
Oh, okay.
So how would shifting my methods to a system like yours be actually advantageous or useful?
Advantageous?
Why is yours better?
What's the
What's
benefit?
better? What's better?
What's the
about it?
benefit? What's the benefit?
Advantage. Oh, okay. At this point, I'm trying to explain the new concept system.
Mhm.
After this, I will give immediately. I will give the new methodology I developed. Yeah, and then you will understand how to reconstruct the methodology, use the new criteria to do model selection or statistical decision. How to select how to determine the parameters of your model.
So how do you have an example of that?
Yeah, well, I have. I will give you. I'll give you immediate.
Okay.
Yeah.
Ligang,
They wait. Take a
you have this room until 11:30.
11:30.
Yeah.
Okay.
And then some.
They wait. Okay. Definition: differentiality, similarity, and linkage. We need to define this. For any two constants, random constants, their differentiality can be defined in this way. If the range of the attribute is known, the R is the range of a random variable. You use the current terminology. Yeah. If the R is unknown, we can use this formula to define the differentiality of any two random constants or any two random measurements. The similarity can be defined as 1 minus differentiality. Linkage. We often, for example, we have experiment. One group, no treatment. The other group has treatment. We want to know some clinical examination. If the clinical examination is has some linkage to the treatment or untreatment, then we have expectation for one group, the other, one experiment for the other. Then their linkage to the treatment or untreatment can be defined in this way. It is measured in the range -1 to +1.